Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to use the policy gradient method again for continuous mountain car, but this time we are going to actually use gradient ascent. If you don't want to try to code this yourself, the relevant file in the course repo is pg_tf.py in the mountain car folder. So one thing you'll notice is that the structure of this file is very similar to the random version. In fact, the architecture of the model is exactly the same. It's just the way we are training them that is different. So at the top we have our hidden layer class, which is exactly the same as before. So let's scroll down. Next we have the policy model class, which models pi of a given s. It takes in an array for the hidden layer sizes, although for our purposes, this will just be an empty array since we'll be using the RBF kernels and a linear layer on top. After we create the hidden layers, we create a final layer to output the mean and a final layer to output the standard deviation. Note that the activation function for the standard deviation is a soft plus to ensure that it's always positive. Next, we create placeholders for the data. So we have x, which represents the input states, actions, which is a 1D array of actions we took in those states, and advantages, which is another 1D array that we'll be calculating externally. Next, we can pass x through the hidden layers to get the second last layer value, and then put that through the final mean layer and the final standard deviation layer to get the parameters of our Gaussian action distribution. We also add a little bit of smoothing to the standard deviation, which is common when you're dealing with Gaussians. Next, because neural network layers always deal with two-dimensional data, we have to convert the means and standard deviations back to 1D arrays. From here, we can create a normal distribution object with these means and standard deviations, and then draw a sample from them. We clip these values to be between -1 and +1, since the environment requires us to do so. Next, we calculate the cost, which is actually the negative of our policy objective, but we need something to minimize since Tensorflow doesn't have a maximize function. Also note that we regularize our costs by adding a constant times the entropy of the Gaussians. By trying to increase the entropy, what we're saying is that we want a larger variance. So this does something similar to the variance smoothing you saw earlier. Next, we have our usual set session function and partial fit, which does one iteration of gradient descent. After that, we have our predict function and sample action functions, which just gives us an action from the current policy. Next, we have our value model class. Unlike the random hill climbing script, we need to model the value as well, because that's used in our calculation of the advantages, which is ultimately used to calculate the policy objective. This is opposed to the hill climbing situation, where all we did was parameterize the policy and then pick the policy that gave us the best reward. So this is very similar in structure to the policy model. We have a number of hidden layers and then a final linear regression layer to predict the value. Nothing much new in here. We use the squared error for our costs and minimize it using atom. Next, we have our set session, partial fit, and predict functions, pretty much the same as the policy model. Next, we have the play1td function. This loops until we get the done signal or until the number of iterations hits a maximum threshold. So depending on your version of Gym, it may cap off at 200, but I found that to be too small to really learn the environment. So if you have an earlier version of Gym, it's probably better. Inside the loop, we select an action from our policy model, do the action, get the next state, and then update both of our models with one iteration of gradient descent. Next, we have our main function. This uses the same RBF feature transformer from earlier with 100 components, and we're using shallow networks in this script. So just linear layers on top of the RBF feature expansion. Next, we play 50 episodes, plot the rewards, plot the smooth rewards. Of course, you can use a different window size because we aren't playing that many episodes. And lastly, we plot the cost to go function. So you're looking for the same hill shape as we've seen previously, although I found these hyperparameter settings to be somewhat inconsistent. So let's run this and see what we get.